Hi class, this is chapter 14.9. We're going to be dealing with pH and pOH scales. So a pH scale is used to describe the acidity of solutions. So how much acid is in that solution is what a pH scale is based on. So a pH of a solution, again, is used to indicate the acidity of that solution. We use a value of 0 to 14, 0 being the most acidic that something can be, if you get here, and if you go all the way here to 14, it is basic. 7 is neutral. So something that would be 6.5 is slightly acidic. Something that's 7.5 is slightly basic. And so that's how we think of 7. And anything below 7 is acidic. Anything above 7 is considered basic. Here's give you some common examples of things that we come into contact with. So, stomach acid, 1.6, lemon juice, 2.2, vinegar, 2.8, soda, if you like soda, here's a good one, 3.0, an orange, apple, tomato, coffee, a potato is 5.8, bread is 5.5. So, when in your reading, that sentence stating, I forgot which section it is, about most of our foods are acidic, this gives you an idea of, yes, it's really acidic. Drinking water, 7.2. Seawater is 8.5. Then we start getting into more cleaner detergents. It's between 8 and 9. Sodium hydroxide, which is known as lye, which is used in some soaps, is 14. 1 molar of HCl solution is 0. So that should give you an idea of this is a strong acid, this is a strong base. Ammonia and so forth. Milk and magnesia, that's similar to Tums, and I forgot what the other ones, and acids, 10.5. So I'm going to show you how to use certain functions on your calculator if you have not done it in a while. Coming into this class, you should have a certain amount of math. Do most students retain that math? Possibly not, but hopefully it'll click on you. But if it doesn't, I'm going to show you. I found this picture online. This is my calculator. I only know how to use my calculator. If you do not have a calculator that matches mine, and you need to figure out where these functions are, you need to look up your calculator, or people do tons of YouTube videos on calculators, and just Google where it is that you're looking for so that you can learn how to use your calculator. I am no use to anybody else when regarding other calculators. I only use a Casio, and I use this one, which is $10. This is all I've ever used. So to do the pH scale, it's a logarithmic scale that corresponds to the concentration of hydronium ions. I'm not going to go into detail about any of that stuff because I'll be honest with you. Most of the students have told me that they get it, but they get enough of it to go forward. And that's all that I care about right here. I'm not going to ask you about most of this stuff. I'm going to ask you about things that you're going to use your calculator to do calculations about, if I ask you questions like that at all. And since we're running out of time, probably not. But you should definitely know how to use your calculator with calculations for these. So I'm going to show you that. So how do we determine the pH? The pH, this is the formula right here. Concentration of hydronium ions. We would plug that in. We use the negative log, and that would give us our pH. So let's take a look at that. So here we have a concentration of hydronium ions that is 1.0 times 10 to the negative 2. So here's my log button. So I would hit negative log. I would enter this in, and it would give me a number 2. Now you have to remember what the sig fig rules are regarding pHs and exponents. I have it on the last page. We'll go over it on the last page. But so your calculator will not give you the correct sig figs. You're going to have to remember the rules if you ever have to add this into, or you're asked about what the pH is, and it's giving you different varies of sig figs. So again, negative log, enter in the concentration. It will give you a pH, but it'll probably give you only one value. You'll have to add in the others. The rules are on the last page of the slide in case anybody doesn't remember what that is. But just in case you didn't remember, you know what, we'll go over it in the end. So a pH scale is a log scale. It's a change of 1 pH corresponds to 10-fold. So it's not just a little, it's the same as earthquakes. Earthquakes, if it's a 5, if it's a 4, it's this, but if it's a 5, it's vastly different. It's way more powerful because I believe the earthquake, how they determine it is also on the same. So let's take a look. pH of 2.0 is 10 times more acidic than 3.0 and 100 times more acidic than a cherry that's at pH 4. So there's a huge increase as the pH changes between each other. It's not little, it's a drastic increase or decrease, depending on which way you're going. Okay, so let's use what we remembered from that calculator to be able to calculate these. So you need to find the log, and you need to find a negative button if that's how it's set up on your calculator. Again, I use Casio. It's all I've ever used. I don't know how to help with other calculators. And if we were in person, I usually have other students help each other because somebody always has a matching calculator. Okay, so calculate the pH of each solution and indicate whether the solution is acidic or basic. We can kind of already figure by looking at the exponents whether these are acidic or basic, but let's just not jump ahead. So here we have a solution for A. We plug it in, we do the negative log, and we plug in our concentration, and it gives us 3.74. pH, remember, anything below 7 is acidic. So this solution is, this solution is acidic. But looking at the exponent here, -4 is it's a very small negative number, so this would be acidic. Okay, let's take a look at the next one. Next one, we plug in the concentration. Our pH is 8.14. It is above 7, so this is a basic solution. But also, just looking at the exponents here, you can tell that this is going to be a basic solution. Okay, oh, what happened? Okay, there we go. Now, I'm going to show you how to do it the opposite way. What if you have the pH, but you want the concentration of hydronium ions? So this is to go another way. This is in your book. This is for another calculator. I'll be honest with you, I don't even know how to make sense of this. This top part, so see where my arrow is? Anything at top is showing you what this is doing. This is explaining the pH is a negative log, so if you have the pH, then you're trying to get this. So basically it's showing you the steps of what is happening, but it's not showing you what you need to do on your calculator. Where my arrow starts is where you need to plug it into your calculator. So this is showing you what's supposed to be happening or explaining how you're using this formula. This is the actual putting it in action. So do you see this little 10x? This is this one. See the 10? This is the inverse of the log. So here we're going to hit shift and you're going to hit log again, but it's going to come up here. It's going to be with the little 10. And then you would enter in negative 4.80. Now you have to enter the negative sign. If you don't, you're not going to get something that's going to it's going to look crazy. So well, you probably wouldn't know that it doesn't match something that what your answer should look like. But if you don't hit negative, your answer is not going to be correct. So make sure that when you do this, you hit shift 10. For me, I would hit negative, and then I would enter 4.80, enter. And that would give me the concentration of the hydronium ions. So there's one way to do it. This is the one I just showed you here, is how to get the concentration of hydronium ions from the pH. And this one, this is getting the pH using concentration of hydronium ions. And this one is getting the concentration of hydronium ions using the pH. So they're just separate, going in opposite directions. Either you want the hydronium ion concentration or you want the pH. So again, shift, it'll get you this 10x. I hit negative, negative's key here, 4.80, and it'll give me my concentration of hydronium ions. If you have one that does not look like this, see if this makes sense to you. Right here, cut it off. This is what you would enter into your calculator. This doesn't make sense to me. I've only ever used a Casio. Okay, so for any solution, we can examine the concentration of hydroxide ions and put that on a logarithmic scale. So here we have, remember, the pH scale gives you an idea, tells you about the acidity of a solution, but it doesn't tell you about the base side of it. So here we have a pOH to determine the concentration of hydroxide ions, and it's the same thing. This one's mine here. So 10, I would do the shift log. It would give me my 10. I would do my negative 8.55, and that will give me my concentration of hydroxide ions. So if you learn how to do it with the acid, it's the same thing. You just have to remember the key thing is you're dealing with hydroxide ions. It's not matching the hydronium ions. And that's something that confuses students. You forget that you're dealing with hydroxide. So if it's asking you for an answer of hydroxide ion concentration and you plug this in, it's wrong because you only gave them the hydroxide ion concentration. You have more steps you have to do. So here is an example of that. So let's say that you're asked for the concentration of hydronium ions, but you're only given the pOH of, you're given the pOH, which is 5.68, not the pH, the pOH. So first thing we have to do is we need to determine the concentration of hydroxide ions. So plug this in, I did. It's going to give me my hydroxide ion concentration. I put a line where the sig fig should be, and because I always do one pass and I do a line underneath as I write to show where I need to keep things. So here is my hydroxide ion concentration. Never round to the very end. This is why I do a line. Never round to the very end, because if you keep rounding each step, your increments are getting further and further away from the actual value. Okay, so now that we have our concentration of hydroxide ions, we're going to jump to another section that I've already covered, which is having to do with water. The dissociation of water constant. Remember, the concentrations of these are equal, and they end up producing, they end up counting, when they're multiplied, it's 1.0 times 10 to the negative 14, which is kW. So now we're going to use that because we have the concentration of hydroxide. We got to figure out what is the concentration of hydronium ions. So plug that in, solve for the solve for the hydronium ions, and our hydronium ion constant is 4.8 times 10 to the negative 9. That's how you can use the pH. It's probably going to ask for a bigger step than just the pH. Or if you're given the pH or pOH, it's probably going to ask for more steps past that. And so this gives you an idea of what the other steps are after. Okay, so the sum of pH and pOH is always equal to 14 at 25 degrees Celsius. So if you're given a pH and you know that you're trying to figure out the pOH, you can use, knowing that it's always up to 14, you can figure out what the other one is. So for instance, if you have a solution with a pH of 3 and a pOH of 11, it's going to be 11. It's going to be 14. It's very simple. And I found this online, so I thought I would put this up. This is just an overall in one place to see all the stuff to determine. Here's the concentration of hydronium ions from the pH. Here's hydroxide ions using the pOH. The pH, you do the negative log, and in pOH, same thing, and then pH plus pOH equals 14. Now, and I pulled this off of another section, how do you remember sig figs? So remember, follow these arrows. This is going to be for the pH. 2 sig figs are after the decimal, or if you have the pH, you follow it back this way. It's going to be 2 sig figs for the concentration when you write it out. So there's another thing to help you with.